A cylindrical grindstone of mass m equals 18 kilograms and a radius of 0.6 meters is initially rotating freely at 26 pi radians per second. That seems pretty quick. Is that pretty quick? It does seem quick. An axe is brought into contact with the grindstone, which brings it to a stop after 30 revolutions. Okay? What is the magnitude of the angular acceleration of the grindstone? Okay. So this is, it may not feel like it, but it's a kinematic equation. So we'll start out by writing our kinematic equations. So acceleration is going to be a constant. V equals AT, x equals 1/2 AT squared plus V naught T plus X naught. And I just memorized these. I have them memorized. The way you derive them is you start with A equals constant, and then you just take the integral with respect to time. And you do that twice, and you get the third equation. Now, there is sort of a fourth equation, more or less. If you solve this equation for t, that's a terrible arrow, tragically bad. That equation for t, and then you plug that t into this equation, rearrange things, you'll get another equation that's Vf squared equals V initial squared plus 2a delta x, where delta x is x final minus x naught. And you might be thinking, well, why don't we just write it then as delta V squared equals 2a delta x. And that's fine too. They're both fine. It's just usually easier to think of distance as a delta as opposed to v squared as a delta, which it's true, they both are, but you don't want to drop this squared part of the v on accident. Okay, focus. So from this point then, we look at how rotational values relate to the linear versions. I know, it sounds complicated. What I mean is acceleration equals angular acceleration times r, v equals omega r, and x equals theta r. So we take this equation, we rewrite it. You might be thinking, wow, how do I know to use this equation? How do I know to use angular? Well, I know to use angular because things are spinning. And I suspect to use this equation because there's no mention of time. Whenever we have two velocities, some acceleration, and no time, then you're like, okay, maybe we're going to use the equation that's absent time. Sans time, as the French would say. Sans temps? I don't know, not important. Focus. So we're writing this equation. We have omega final squared equals omega initial squared plus 2 alpha delta theta. Okay? And you can see that by writing it out and then just seeing that everything cancels. That there's an r associated with, actually there's an r squared associated with each term. There's an r there, there's an r there. When all those r's are canceled, you're left with this equation. So pretty much you can take any kinematic equation and just substitute the linear for the angular. So from this point then we look at, all right, so we know r is 0.6, which doesn't actually matter at this point, so we're probably good. We know initial angular velocity is 29 pi radians per second, so 29 pi. And then I like to write radians in parentheses because it's not actually a dimension. There's no, it's not measured in meters, it's measured in radians, which really aren't a measurement of anything. I guess of spinning, dimensionless. X is brought freely, which brings it to stop. Brings it to stop means that omega final equals 0. Acceleration, I think that's what we're trying to find. What is the acceleration? And it does it over a period of 30 revolutions. So I'm going to say then that d theta equals 30. We could say that theta initial equals 0, theta final equals 30. But all that information really is telling us is that theta final is 30 greater than theta initial. And that means that delta theta will always be 30. So we're good with that. That's one of the reasons I like to write delta theta here, because you see this scenario pop up time and time again. Okay, so plugging these in, we have 0 squared equals 29 squared pi squared plus 2 alpha 30. Okay, and now these both, when we solve for alpha, it looks like we're going to get a negative, which makes sense because we are expecting a negative acceleration. So we'll do 29 squared pi. Actually, I'll just do 29 pi squared. There we go. That way, I only have to square one thing, divided by 60. 2 times 30, and then this will be a negative involved. All right, I think I can do this on my calculator. Calculator, bum bum bum. 29 times 3.1415. I know there's like a pi symbol somewhere. I don't use it. Right there. Quantity squared divided by 60. I'll just do the negative in my head. So we have 138. Oh, 30 revolutions. That's not, okay. We need to convert that to radians first. Okay. Revolutions per second. So 30, that just felt kind of weird. Felt high. 30 revolutions. We got to convert that into radians. So there'll be 2 pi radians per revolution. Okay. So I'm going to rewrite this. This right here is 30 times 2 pi. So we do this again. We have 29 pi squared plus 2, which will be 60, times another 2, which will be 120. 120 pi. 2 times 2 is 4. 4 times 3 is 12. Add the 0, 120. Yep, pi. Alpha equals 0. Actually, it's 0 squared, but you get the idea. Alpha equals 29 pi squared over 120. I'll put the pi squared out here, actually. Pi, one of the pi's cancel. We have 29 squared pi over 120. There we go. That seems better? I don't know. 29 squared times 3.1415 divided by 120. Okay, we get 22 equals 22, and this will be radians per second squared. Put the radians in parentheses. Whoop, there we go. Not necessary, I just enjoy it. Come look over here. Wow, a lot of work. 22. Let's see how close it actually is to 22. 22.017. Yeah, I'll leave it at 22. Yeah, 22.017. That way, in case I need the number later, I can tell. That's supposed to be an S. It's a cursive S. What is the magnitude of the angular acceleration of grindstone? 22. This one right there. Okay. Looking at the others. Whoop. Probably can delete most of that. What is the magnitude of the frictional force of the axe on the grindstone? Okay, so frictional force here, we know force equals mass times acceleration. The angular equivalent of this is torque equals IA, where I is the moment of inertia. And torque also equals R cross F. So here we're going to have a force this direction. We're going to have an R this direction. So I'm going to rewrite this as R perpendicular. The part of R that's perpendicular to F. And you can see that since the axis is being held at 90 degrees there, or as a tangent to the circle, so to speak, that the entire R is going to be perpendicular. So this is just going to be R F. And you can also think of this as the sign between the two. And since theta in that case would be 90, not to be confused with theta up here, 90, it would become 1. I'll call this phi. Does that make it that better? Maybe that's better. Okay. But we haven't really talked about this moment of inertia yet. Let's go to Wikipedia. Nope, that's Wolfram. Let's look up moments of inertia. And there's basically it's a table. You can figure these out. Ooh, that's a cool picture. Ooh, Russian Museum. That's probably why it's so cool. Okay, let's see. There's probably some sort of table of such. Table. Wow, there's a lot. Maybe there's a list. List of moments of inertia. Haha, good for me. So we have a disk. So the ones that will be important here in life is just a dot. If you have a dot rotating about a point, it's going to be mr squared. And that's going to be the same as a cylindrical shell. This is an infinitely thin cylindrical shell. And then we're going to have a disk. Did I pass a disk already? Nope, right here. This is where a disk is. So the one you're going to be most concerned about is with the z-axis, 1/2 mr squared. And that's the case we have here. So where the disk is spinning. One other thing to keep in mind is, this one's cool too. If you have like basically a rod spinning, it's 1/12 ml squared. And the other one is going to be, you're going to learn about the parallel axis theorem. That also involves mr squared. Okay, so we have our answer here that we want is 1/2 mr squared. Go back to the problem. So we have torque equals 1/2 mr squared times alpha equals r times F. We're looking for the force in this case, so one of the r's will cancel. And we're left with force equals 1/2 mr alpha, which is, we're told, a mass of 18 kilograms. So 1/2 times 18 times 22 will give us the force involved. Go back to our calculator. Hopefully something's still up. Aha, it is. So second answer times, I was going to say times 9, because 1/2 times 18 is 9, times 22 is 4359. That seems like a lot. 4359. That does seem like a lot. Did I do something wrong? 1/2 mr squared. What is the magnitude of the numerical force? I think I did the 22 twice. Divided by 22. 198. See, that's something possible? Nope, that's not even possible either. Something is amiss. So it looks like I forgot the R. Should have known. So this will be put in 0.6 as well. Okay. So now really doing the problem. This time it's for reals. So we'll do 22. Nope, start at the left. Don't get cocky. 0.5 times 18 times 22 times 0.6. 118.8. 118.8. There we go. And that's a possible answer. 119 newtons. All right. So all the hard stuff totally did fine. When it came to plugging into the calculator, tragic. So the story is try and simplify everything as much as you can on paper first, and then put simple numbers into your calculator. And don't forget those simple numbers. Okay. Now, we're trying to find out what is the direction of the torque due to the frictional force of the axe on the grindstone. Okay. So this is just a math thing. So you have to know, yes, you should know that torque equals R cross F. That's just something you memorize. Take a piece of paper, write it down like 50 times until it's just burned into your soul. And from here then, we just look at it from a math point of view. you should know how to do cross products. So drawing this out, we have the force is going to be this direction because it's slowing down. Putting the axe on there is slowing down the rotation. R, I'll do a different color. R is this direction. So when you do R cross F, you do, maybe this way. Nope, this way. R, I guess this way is better. Okay, focus. R cross F, it's going to be into the page. So take your hand, point in the direction of R, which is the first value, bend your fingers in the direction of the second value, which is F, and it'll be into the page. So it'll look like that, torque. So torque equals R cross F, and they only give us one Z value, and it is into the page. And also, you know that whenever you take the cross product of one vector and another vector, the resultant vector will be perpendicular to each. And since both the R and the F are on the X and Y plane, the resultant vector will be in neither of those. The only one left, assuming 3 dimensions, is the Z plane. So when I have one option that's a Z, it's going to be the Z. And that's why. Okay, that's how this problem is approached. To backtrack a little bit, kinematic equations, you basically do the analog version, angular version of kinematic equations, which is the angular is the analog of the linear. That's fine. We then relate torque and force, and we also use the angular version of force equals mass times acceleration, which is torque equals moment of inertia times angular acceleration. We need to find the moment of inertia of a disk, 1/2 mr squared. Plug that in, solve, and then at the last question, they ask us to basically look at the definition of torque equals radius times, or with the cross product of radius and force. Hope that helped. See you next time.